gaseous form. All right, this is going to be one of the problems of zero. Not only does it shut down 80,000 horsepower of ship, it does other things. All right, let's consider this. We'll let A and B both be equal to 1. All right? So since A and B are equal, we can say that B squared equals AB. Right? All right, y'all are doing this. This is basic stuff. That's equation 1. You might want to note that it's equation 1 on your paper. Don't write down all the rest of the stuff. Just write down and put it. All right, since A equals itself, then it's obvious that A squared equals A squared. All right? If it's equal to 1, 1 squared equals 1 squared. All right, it still works there, equation 2. If we subtract equation 1 from equation 2, this gives us A squared minus B squared is the same thing as A squared minus AB. All right, very simple stuff. Now, factoring. I got to hear y'all here. I got to hear somebody say factoring just a minute ago. I was like, all right. That was kind of cool. Let's factor both sides of the equation. A squared minus AB equals A times A minus B. All right? Likewise, A squared minus B squared equals A plus B times A minus B. Substituting that into equation 3, this is what you're going to get. All right? Pretty simple so far, right? Follow me? Haven't lost anybody yet. Good. Because I'm going to lose myself here pretty soon. Okay. Let's divide both sides of the equation. We need to go back one? Okay. All right. I need like Jeopardy music or something playing in the background. All y'all writing this down. All right, so equation 4 gives us this nice, lovely little A plus B times A minus B equals A times A minus B. All right. We're all clear. All got it. Okay. Get notes from your friends if you get lost. Okay. Now let's divide both sides of this equation by A minus B, and there's what you're going to get. A plus B equals A. It's equation 5. Subtract A from both sides. A equals 0. It's all very logical. All works quite well. It's equation 6. But we set B to equal 1 at the beginning of this. Beginning of this proof. So that means 1 equals 0. Okay? Follow along. We've done this mathematically. You can go back and check your math. It's all there. All right, so equation 7. 1 equals 0 by the time we've got to this point. Okay. So 1 equals 0 is an important point. We know that Snooky has 1 head, but 1 equals 0 by equation 7. So that means Snooky has no head. Likewise, Snooky has 0 leafy tops. Therefore, she has 1 leafy top. Multiplying both sides of equation 7 by 2, we see that 2 equals 0. Snooky has 2 legs, therefore she has no legs. Snooky has 2 arms, therefore she has no arms. All clear so far? It gets better. Now, let's multiply equation 7, so you can look back up at your thing, and we'll multiply it by Snooky's waist size. All right? And then we'll say with Snooky's waist size by equation 7, so that Snooky's waist size equals 0. That means that Snooky tapers to a point. All right? This is where Furnace Shelley, all right, this whole point thing, this whole perspective thing, means Snooky tapers to a point. Now, what color is Snooky? Take any beam of light that comes for her and select a photon. Multiply that by equation 7, that equation 7 by the wavelength, and we see that Snooky's photon wavelength equals 0. All right? And Dr. Hastra has a copy of this file slide too. So but by multiplying equation 7 by 640 nanometers, which is one of the color scales, just arbitrary color scale in there, we see that 640 equals 0. All right, we multiply it by equation 7. Combine equation 10 with equation 11, we see that Snooky's photon wavelength equals 640 nanometers. That means that this, or any other photon that comes from Snooky, is orange. That would be the wavelength orange. Therefore, Snooky is orange. Right? Gets better. To sum it up, we've proved mathematically that Snooky has no arms and no legs. Instead of a head, she has a leafy green top. She tapers to a point, and she has a shade of orange. Clearly, then, Snooky is a carrot. Adding 1 to both sides of equation 7, we see that 2 equals 1. Snooki and a carrot are two different things. Therefore, they are one thing. All right? This is solid mathematics. There's absolutely nothing wrong with this math. Actually, what's wrong with this proof? Only one thing. Equations 4 to 5. When we went there, we divide by a minus b. But since a and b are both equal to 1, then a minus b equals 1 minus 1 equals 0. We divide it by 0, and we get the ridiculous statement that 1 equals 0. All right, within this mathematical proof. From that, we can prove any statement in the universe. All right, we can prove that George Washington was a camel. All right, we can prove anything we want to. We can prove that my failing grade in calculus is actually an A, plus. All right, we can do anything. 0 has the power to destroy logic. And this is where the concept becomes important to us. Most cultures reject this. In the Thai culture, they would consider this a form of mental illness. We're thinking too much about this. Thinking very much is a sign of mental illness. The Thai have a phrase, "Mai pen lai," which means don't worry about it. Okay, don't worry about it. Okay, the whole concept of 0, "Mai pen lai." All right, don't worry about it. It doesn't make any sense. You don't need it. All right, you're not going to count it. How many times in your life have you been called upon to measure a board of 0 inches? All right, it just doesn't happen. How many times have you been called upon in your life to measure a board of negative 23 inches? It doesn't matter. All right, 0 gives us some fits. Okay, it gives us some issues to work with. That's it. Confused? Ready to reject 0 right out?
Don't you do
okay. You can't. Modern mathematics, we can't do modern mathematics without 0, and you can't do perspective drawing without 0. Right, they're all part of the process. And I ran over my time.
Actually, we do have class till 6:50. We ran over time till break.
Okay.
So what we might want to do is open it up to questions, and then after that, we can just, if you guys want to leave early, you can, or if we keep talking, we can keep talking. And possibly just leave early without taking a break, unless you guys need a break now.
So what's with the chips? What's with the chips?
Oh, that's yourself. No, actually, I'm going to have those back. But the chips represented your stuff. All right, the hunters and gatherers, that represented your stuff. All right, that's your bananas, that's your fish, that's your boy. Even if somebody comes and takes all of them away, there are people in here who have more than the 3 chips that they got, or just feel generous, they're going to give you something. All right, going back to that one, the concept of reciprocity.
I need to pass in.
Somebody else.
Oh, thank you. Throw them up there and like slow down. I feel like I should. So what are... Never mind.
Ask.
You got to ask it. You already said what are.
I have a question. I don't really understand the mind. You're saying it was I guess I just don't fully understand. They used it, but it was a setting position for the calendar, so that was part of it. Like they actually had, like it was one of the months. Was that the 5 month? Or 5
It's one of the days. I mean, they don't say 0 set, they'll say the seeding up. So basically the beginning. And that's one of the things where our calendars come into problems. All right, y'all remember the millennium. All right, it hasn't been that long ago. For most of us, it hasn't been that long ago. For some of you, it seems like a decade ago. The millennium. What happened with that? Because our calendars didn't start with year 0, we got kind of weird on things. And so people started booking vacations for December 31st, 1999 to celebrate the new millennium on January 1st, 2000. No. January 1st, 2000 was 1,999 years since the calendar started. The real millennium began in 2001. The Maya got away from that by starting their calendars with 0 and using that as a starting point for their numbers. Things work out within the calendar. And their calendar goes in 13-year cycles, and then 4 13-year cycles is a century with them. For those of you that are worried about the Mayan calendar running out in 2012, there's a reason why it runs out. It resets. In 2012, it resets. The Maya scholars, I give them credit, they put a calendar out for 1,000 years in advance and finally said, okay, that's enough work. Right? That'd be like, how long can you factor out these equations? You finally get to the point, okay, that's enough work. Right, you're good.
They didn't have television though.
Yeah. They didn't have television. But it's amazing to think with the Greeks, what the Greeks were able to accomplish without 0. All right, things today that we figure, I mean, our math requires us, we've got to have zero, we've got to have infinity. The Greeks, the Babylonians, Romans, I mean, the ancient cultures, all without zero, but still created some fantastic things. Zero opened up some doors. Zero also opened up something that came about in Europe that didn't come around the rest of the world, and that was the development of the scientific method. All right, if you look at the timing of the development of the scientific method, it and the appearance of zero correspond to each other, because zero now meant you could play with numbers. You could think in abstract terms. It didn't all have to have real applications. You could think of bizarre little things and you could test it with the numbers. And that kind of comes out with our concept of testing things in science as well.
If the Greeks didn't have zero, does that mean that basically zero isn't involved in architecture?
Exactly. Exactly. Again, Pythagoras, they knew about zero to an extent, but they didn't want to work with it. All right? Because of all the reasons we have in there, it violates things. It doesn't add to it. It doesn't take away. You can't use it. It didn't seem practical to them. Greek merchants would never use zero because they weren't interested in that. They were interested in how many things you have on hand, and nobody has zero things on hand. Pythagoras actively rejected it. Archimedes rejected it, even writing his description of the universe, rejecting the whole concept of infinity as well. In our early Christian world, our early concepts of God followed on Archimedean principles that say, well, no, you don't have nothing, and you don't have infinity. It's not until later in the Renaissance that scholars start challenging that and say, well, no, you can have void. You can have nothingness. Yeah, the Greeks accomplished wonderful things without the use of zero. Geometry is fantastic. Geometry and trig are my two favorite forms of mathematics. I love working with them. It's one of those geeky things I do. I got this thing one time. It's called the world's hardest, easiest geometry problems. That ask any seventh grader, they can tell you how to solve it. I started looking at the thing. I went to the bookstore and bought a new protractor and got that out. And I spent 4.5 hours working on things. I didn't finish the proof. And I'm like, I'm not even in geometry class anymore. Yeah, who cares? It's well, it's taking time off from regular work.
The golden 1.616 or something like that, what is that? I've never heard of that before.
The golden ratio. And I'll give you my explanation of it, and then Dr. Hastert can give you the real mathematical explanation of it. Pythagoras, and you can look the golden ratio up online. There's a couple of things. Pythagoras gets a lot of credit for some things, and a couple of things he gets overlooked on is the golden mean. He was the first to figure out musical instruments that you could have certain tones that were complementary to each other, working with things. The golden ratio is something they found that it occurs in nature. All right? It occurs in nature over and over again, that you've got this proportion. And that's what the Greeks were into. They're into proportions. They're into ratios. That's why they didn't like zero, because zero blows out ratios. You just can't have it. They didn't really like irregular numbers because it came in there. It kind of violated some of the norms that they worked with. If you look in nature, there's a balance. If you look at people's, what we consider, if you look at magazines, you look at what we consider an ideal face, the way things are set up, and you measure the width between the outside edges of the eyes and the width from the top of the eyes to the chin. This width is 1. This width is almost always 1.6 something times that 1. That proportion exists. If you look at the spiral rings on a pineapple, their ratio is 1 ring to 1.6 rings on the measurement. Take the nautilus, the sea snail. Each chamber is 1.6 times larger than the previous chamber. All right, this is something that came up. The golden ratio came up within bringing it back to architecture. The width times length. The ideal width of the building being set at 1 unit, the ideal length is 1.6 units. We still use that today in my outside fields in architecture and historic preservation. We still use that standard today when figuring out buildings. This became, and this was where part of this concept of numbers being magic. They looked at Pythagoras and his students, all right, the people that learned from him. They were looking for this pattern over and over again in nature. They were looking for it everywhere they turned. They found it. Fibonacci, again, the sequences of numbers. 1, 1, 2, because 1 and 1 is 2. 3, 1 and 2 is 3. 5, 2 and 3 is 5. 8, 3 and 5 is 7. 8 fifths is 1.6 some set of numbers. 13/8 is 1.6. I mean, Fibonacci coming along almost